the Fermi Paradox, and Earth's unique geology. The universe is a vast ocean of stars. The universe is a vast ocean of stars and planets, stretching beyond our imagination, and yet bound by the same physical laws that govern our tiny blue world. Within this ocean lies a paradox so powerful that it has challenged some of the brightest minds of science for decades: the Fermi Paradox. It begins with a simple yet profound question posed by the physicist Enrico Fermi. Where is everybody? With billions of stars in our Milky Way galaxy alone, and an even greater number of planets orbiting them, many within the so-called habitable zone, it seems statistically inevitable that intelligent life should have emerged elsewhere. Yet, despite our increasingly advanced telescopes, satellites, and listening devices, we have found no concrete evidence of alien civilizations. The silence is deafening. Why does the galaxy, so full of potential, remain so empty in reality? One explanation may lie beneath our very feet, in the restless and living geology of our planet. For while astronomy often focuses on stars, planets, and atmospheres, there is a deeper question of what makes a planet not just habitable, but capable of sustaining complexity, diversity, and intelligence. This is where Earth's unique geological engine, plate tectonics, enters the story, not merely as a background feature of our world, but as one of the main reasons we exist at all. Plate tectonics refers to the movement of massive slabs of rock that form Earth's outer shell. They collide, pull apart, and slide past one another, creating mountains, triggering earthquakes, and fueling volcanoes. More importantly, they act as a planetary recycling system, pulling carbon from the atmosphere and locking it in rock, only to release it again through volcanic eruptions. This endless cycle stabilizes Earth's climate across millions of years, keeping it within the narrow range where liquid water and life can exist. Without plate tectonics, Earth would be a static, dying world, its nutrients locked away in rock, its climate swinging wildly between extremes. Mars and Venus are sobering reminders of what happens when a planet lacks such geological vitality. Mars, once wet and possibly habitable, lost its internal heat and became geologically dead. Venus, our so-called twin, developed a stagnant lid that trapped its surface under suffocating heat and crushing atmosphere, dooming it to a runaway greenhouse effect. Earth alone developed the delicate dynamic balance necessary for complexity to flourish. If plate tectonics are rare, then complex life may be rare as well, and the Fermi Paradox begins to make sense. It is not enough for planets to simply orbit within a habitable zone. They must also possess the geological dynamism to regulate climate, recycle nutrients, and sustain biological diversity over billions of years. Earth's geology is, therefore, not just the stage for life, but an active participant in life's story. Our mountains, oceans, and volcanic eruptions are not accidents. They are the heartbeat of a living world. This realization transforms the search for extraterrestrial life. We are not merely looking for worlds with liquid water and the right temperatures. We are searching for worlds with restless crusts, internal heat, and the capacity for tectonic renewal. Perhaps this is why we have not yet heard the voices of others. Intelligent civilizations may be far rarer than we thought, not because life itself is impossible, but because the specific geological conditions necessary for life to become intelligent are profoundly scarce. As we look to the stars, we must remember the ground beneath our feet, for it may hold the ultimate key to the silence of the cosmos. Plate tectonics, Venus and Mars. Why Earth is rare. Earth's defining feature, one that sets it apart from nearly every other planet we know, is its restless and dynamic crust driven by the invisible hand of plate tectonics. And to truly grasp why this matters, we must look not only at Earth itself, but also at our two closest planetary neighbors, Venus and Mars, both of which reveal what happens when tectonic forces either fail to ignite or collapse into stagnation. Because while our own planet shudders with earthquakes, erupts with volcanoes, and builds mountains that scrape the sky, Venus and Mars stand as geological cautionary tales, frozen in states that make them inhospitable to complex life. And by comparing them with Earth, we begin to understand just how rare our situation may be in the cosmos. Plate tectonics is not simply a geological curiosity. It is the great regulator of Earth's climate, the conveyor belt of essential nutrients, and the architect of biodiversity. It is the hidden system that continuously recycles carbon dioxide between the atmosphere, oceans, and rocks, preventing catastrophic climate swings that could wipe out fragile ecosystems. It is the process that brings phosphorus, potassium, and other life-sustaining elements back to the surface again and again, so that plants, microbes, and eventually civilizations can flourish. And it is the unseen force that creates mountains, islands, deep ocean trenches, and a mosaic of habitats where evolution can run its endless experiments. Without plate tectonics, Earth would eventually choke on its own carbon dioxide or freeze into lifelessness, because no planet can remain habitable for billions of years without some internal mechanism of renewal. Yet, as common as rocky planets are in the galaxy, tectonic activity seems to be anything but common. Take Venus, often called Earth's sister planet, because it is nearly the same size and mass, orbiting not much closer to the Sun than we do. At first glance, Venus should be a twin, perhaps even a second cradle of life. But its surface tells a different story. Venus is smothered beneath a suffocating atmosphere of carbon dioxide, its surface temperatures soaring to nearly 900 degrees Fahrenheit, hot enough to melt lead, while sulfuric acid clouds swirl above. Its surface is not fractured into moving plates like Earth ETDs, but is instead locked in what scientists call a stagnant lid regime, meaning the crust behaves as a single immobile shell that never recycles, never renews, and never breathes life back into the atmosphere. The lack of tectonic cycling doomed Venus to a runaway greenhouse effect, where carbon built up endlessly in the atmosphere with no way to be drawn down. And the result is a hellscape that stands as a stark warning of how delicate planetary balance truly is. Mars tells another cautionary tale, one of stillness rather than suffocation. Smaller than Earth, with only a third of our planet's gravity, Mars cooled quickly after its formation, its internal heat leaking away into space. Without sufficient heat to drive convection in its mantle, the planet lost its tectonic dynamism and settled into geological silence. In its youth, Mars may have hosted rivers, lakes, and even oceans, and its surface still bears scars of massive volcanoes, such as Olympus Mons, the largest in the solar system, and vast canyons like Valles Marineris, dwarfing Earth's Grand Canyon. But these were relics of a more active past. Today, Mars is a cold desert, its atmosphere thin, its core nearly lifeless, and its crust rigid and immobile. Without plate tectonics, Mars could not regulate its climate, could not recycle nutrients, and could not sustain the conditions for life beyond the microbial, if even that. These two worlds, Venus with its stagnant lid, and Mars with its geological death, stand in sharp contrast to Earth's living crust. And this contrast tells us something profound. the conditions necessary for plate tectonics, and therefore for long-term planetary habitability, are incredibly specific. A planet must be large enough to hold internal heat, but not so large that its crust locks into immobility. It must possess the right mix of radioactive elements to generate internal energy over billions of years. It must have enough water to lubricate its plates and enable subduction, the process by which one plate dives beneath another, carrying carbon and other elements into the mantle. Water in particular may be the secret ingredient. On Earth, it not only shapes the surface through erosion and oceans, but also weakens the lithosphere, making it possible for plates to crack, slip, and dive, fueling the tectonic engine. Without oceans, subduction may never begin, and without subduction, plate tectonics may never arise. That delicate interplay of size, composition, heat, and water may be so rare that Earth's geological fortune is almost miraculous. And if complex life requires active tectonics, then intelligent civilizations could be as scarce as diamonds in sand. The silence of the universe may not mean that life is absent, but that life capable of building radio telescopes and starships demands conditions that almost never align. When we look at Venus and Mars, we are not just seeing barren neighbors. We are seeing two possible fates Earth itself might have endured if circumstances had tilted even slightly differently. If Earth had cooled too fast, we might have become a frozen desert like Mars. If our atmosphere had thickened too much, we might have been smothered like Venus. Instead, Earth balanced on a razor's edge, with tectonic activity breathing stability into its climate for billions of years, long enough for life to move from microbes to forests, oceans, and eventually human civilizations. The implication is staggering. The very existence of humanity may rest on geological luck. For astronomers searching for life beyond our solar system, this lesson is crucial. A planet's distance from its star, its size, and even its atmospheric composition are only part of the puzzle. Without internal dynamism, without the churn of mantle convection and the restless dance of plates, the surface may be sterile, its climate unstable, its potential for complexity extinguished before it begins. This is why the study of Venus and Mars is so important. They remind us that habitability is fragile, and that while planets may be common, worlds that can cradle civilizations may be rare jewels scattered thinly across the galaxy. Earth's geology is not a given, it is a privilege. And in recognizing this, we may finally begin to understand why the universe feels so quiet. The Drake equation and geological role in civilization. When astronomer Frank Drake introduced his famous equation in 1961, he sought to transform the profound mystery of extraterrestrial civilizations into a framework of measurable probabilities, breaking down the question, are we alone? Into a chain of factors that could, at least in theory, be estimated by science. And while the equation has inspired generations of researchers, each term still carries enormous uncertainty. Yet what is becoming increasingly clear is that the equation, originally focused on astronomical and biological factors, may be incomplete without geology, because the presence of active plate tectonics may be as critical to the survival of advanced life as liquid water or sunlight. And to ignore it is to overlook one of the most fundamental regulators of habitability. The classic form of the Drake equation includes several factors: the average rate of star formation in the galaxy, the fraction of those stars that have planets, the number of planets per system that might support life, the fraction of those planets where life actually emerges, the fraction of life-bearing planets where intelligence arises, the fraction of intelligent civilizations that develop detectable technologies, and the length of time such civilizations remain detectable before vanishing. Each step narrows the pool of candidates, and depending on how optimistic or pessimistic one's estimates are, the outcome ranges from a galaxy teeming with civilizations to to one where we are the only voice. Yet, as astronomers refine their estimates with new data from missions like Kepler, TESS, and the James Webb Space Telescope, one striking reality emerges. Habitable planets may be common, but geologically active planets capable of sustaining stability for billions of years may be exceedingly rare. Plate tectonics, as we've seen, is not just about earthquakes and volcanoes. It is the thermostat of a planet maintaining atmospheric balance by cycling carbon dioxide between the air oceans and crust, a mechanism that has kept Earth's climate within life-friendly bounds for over 3 billion years, despite fluctuations in solar output and catastrophic impacts from space. Without this stabilizing feedback, a planet may spiral into extremes, too hot like Venus, too cold like Mars, before complex life ever has a chance to emerge. This means that the fraction of planets where life arises, often denoted as FL in the Drake equation, might be high, since microbial life seems resilient and adaptable. But the fraction of planets where intelligent civilizations develop, Fi, could be far lower if tectonic regulation is a prerequisite. Moreover, even if intelligence arises, its survival and technological flowering may depend on geological cycles that recycle nutrients and create diverse habitats. Consider the role of mountain ranges, island chains, and ocean basins in driving evolutionary innovation on Earth. These tectonically generated features have repeatedly isolated populations, forced adaptation, and sparked biodiversity. Without them, evolution might stagnate in a uniform world with fewer ecological pressures. The recycling of phosphorus and potassium, essential nutrients for DNA and energy transfer, also depends on tectonic processes exposing fresh rock to erosion. Without this continual renewal, ecosystems might collapse long before intelligence could develop. Thus, geology directly influences not only whether life can survive, but also whether it can thrive to the point of becoming technological. Some scientists argue that by incorporating geological activity into the Drake equation, we must dramatically lower the estimates for advanced civilizations. If, for example, only a small percentage of planets possess sustained tectonics over billions of years, then the cosmic silence described by the Fermi Paradox becomes less surprising. It is not that life fails to arise, but that it rarely endures long enough or diversifies deeply enough to reach radio telescopes and starships. This perspective reframes our expectations. Instead of imagining the galaxy as brimming with advanced civilizations, we may need to picture it as a vast ocean dotted with microbial reefs, but almost devoid of the towering structures of intelligence. The silence, then, is not a mystery, but an inevitable consequence of geology's rarity. Yet, this does not make the search futile. It sharpens it. If we know that tectonics matter, then our strategies must change. When analyzing exoplanets, we must look not only for atmospheric signs of water and oxygen, but also for indirect clues of geological activity, such as volcanic gases like sulfur dioxide or unusual heat signatures detectable in the infrared spectrum. The James Webb Space Telescope and future missions like NASA TOVI's Habitable Exoplanet Observatory may soon allow us to detect these fingerprints, narrowing the search to worlds that share Earth's dynamic vitality. Imagine updating the Drake equation with a new term, FG, the fraction of planets with sustained geological recycling. Such a term could transform our estimates, showing that while microbial life may pepper the galaxy in vast numbers, intelligent civilizations are staggeringly rare, perhaps numbering only in the dozens across billions of stars. This stark revision underscores why humanity's own survival is intertwined with geology. Without tectonics, Earth itself might not have remained habitable long enough for us to evolve, and without an awareness of how fragile this balance is, we may not safeguard our world for the future. In this sense, The Drake equation is not just a tool for estimating others, but a mirror reflecting the conditions that made us possible. It reminds us that our place in the cosmos may be the result of both astronomical abundance and geological scarcity, a combination that renders us precious and perhaps uniquely responsible as caretakers of intelligence in a silent galaxy. The search for extraterrestrial civilizations is therefore also a search for ourselves, a quest to understand the unlikely fusion of physics, chemistry, biology, and geology that brought forth consciousness on this small blue planet. And as we look outward, listening for faint signals across the stars, we must never forget that the strongest signal of all may be the restless rumble beneath our own feet. Exoplanet Search, James Webb Telescope, and Geological Clues. The search for exoplanets. Those distant worlds orbiting stars far beyond our sun has become one of the most exciting frontiers in modern science. And while the discovery of thousands of such planets in recent decades has revolutionized our understanding of the universe, the true challenge is not just finding them, but identifying which of them could truly support life, and more specifically, complex, intelligent life. With missions like NASA's Kepler and TESS, we now know that planets are abundant, and that many exist within the so-called habitable zone, the region where temperatures allow liquid water to persist. But this is only the beginning of the story, because habitability depends on far more than distance from a star. It requires stable climates, renewable nutrient cycles, and geological vitality. This is where instruments like the James Webb Space Telescope, JWST, step into history, providing humanity with an unprecedented ability to peer into the atmospheres of these distant worlds, searching for chemical fingerprints that hint at both biology and geology. Traditional detection methods like the transit method, which measures the dimming of starlight as a planet passes in front of its star, and radial velocity, which detects the gravitational tug of planets on their host stars, give us information about size, mass, and orbit. But they tell us little about the deeper qualities that matter for habitability. JWST and future telescopes go further by performing transmission spectroscopy, analyzing starlight as it passes through a planet's atmosphere during transit, leaving behind subtle absorption lines that reveal the presence of specific gases. Some of these gases, such as water vapor, methane, and oxygen, could indicate biological activity, while others, like sulfur dioxide or carbon dioxide in certain contexts, may reveal geological processes such as volcanism. This is critical because active volcanism is a hallmark of an energetic interior and may be a sign that tectonic activity is alive and well, feeding a planet's long-term habitability. The detection of these signatures is not easy. Planets are faint, stars are bright, and signals are weak. But advances in infrared technology allow JWST to separate these tiny clues from the glare of their stars. Already, early observations have suggested unusual atmospheres on several exoplanets. And while none are yet confirmed as Earth-like, each discovery brings us closer to identifying the rare few that might mirror our dynamic home world. Beyond atmospheric chemistry, scientists are also exploring ways to detect thermal emissions from exoplanets. A planet with active geology may emit heat from its interior, detectable in infrared as localized hotspots or unusual global warmth, inconsistent with simple models of starlight absorption. Such heat could point to volcanism, tectonic stress, or other processes essential to recycling elements and stabilizing climate. Meanwhile, computer simulations provide another tool, modeling how planetary size, composition, and orbital characteristics influence the likelihood of tectonic activity. By feeding real observational data into these models, researchers can predict which exoplanets are most promising for follow-up observations. Future missions such as the European Space Agency, S-Ariel, and NASA Euriket planned Habitable Exoplanet Observatory, HABEX, are designed to push these investigations further, offering more detailed measurements of atmospheric gases, climate systems, and potentially even surface features. Imagine detecting sulfur compounds that suggest active volcanoes, or subtle variations in atmospheric carbon dioxide that imply long-term carbon cycling. Such discoveries would not just hint at geology, they would point to the very processes that make planets alive in the deepest sense. If we could confirm that an exoplanet has both liquid water and active tectonics, it would instantly become one of the most important objects in the sky, a candidate not just for microbial life, but for the eventual development of intelligence. The implications stretch far beyond science. Discovering a planet with Earth-like geological dynamism would be a monumental step toward answering the Fermi Paradox, suggesting that, while rare, we may not be entirely alone in the galaxy. Yet here lies the sobering possibility. As powerful as JWST and its successors are, they may find that most planets, even those in habitable zones, lack the signatures of tectonic renewal. We may see countless frozen worlds locked in geological stillness, or suffocating planets smothered by runaway greenhouse effects. Such outcomes would reinforce the idea that Earth is not just one of many, but one of very few. And yet, even a single detection of volcanic outgassing, even one confirmed world with a breathing geology, would change everything. It would tell us that the spark of complexity is not unique, that the geological solution to the Fermi Paradox is not absolute, and that somewhere out there, perhaps separated by thousands of light years, another planet may already be nurturing the seeds of civilization. As we refine our instruments and expand our search, we must also expand our imagination. Signs of life and geology may not always look exactly as they do on Earth. Alien tectonics may operate differently, producing gases we do not immediately recognize, or habitats unlike any on our planet. Our challenge is to distinguish true signals from noise, to avoid both false hope and undue pessimism, and to steadily build a picture of the cosmic distribution of habitable worlds. In this endeavor, international collaboration will be vital, with space agencies, observatories, and researchers across the globe pooling their data and expertise. The search for life is no longer the dream of a few astronomers. It is a global scientific project, uniting humanity in its oldest question: are we alone? JWST represents only the beginning of this journey. The extremely large telescope under construction in Chile, the Roman Space Telescope, and other future giants of observation will extend our reach, allowing us to probe smaller, Earth-sized planets with even greater precision. With each new dataset, we refine the Drake equation, adding geology as a critical factor and narrowing the probability space of civilization. And as the evidence accumulates, we may find ourselves forced to confront the possibility that we are either profoundly rare or on the cusp of discovering neighbors in the vastness of space. Either way, the search itself changes us. It reminds us that Earth is a miracle of geology, that our restless plates are not just natural disasters, but the foundation of our existence, and that in understanding the forces that sustain us, we gain both humility and responsibility. Whether the galaxy remains silent or begins to whisper back through the atmospheres of distant worlds, the quest will endure, driven by the same curiosity that led us to look up at the stars in the first place. The Hoag's object galaxy. Mystery among the countless galaxies scattered across the universe, most fall into familiar categories. Spiral galaxies like our Milky Way, with graceful arms winding around a bright core. Elliptical galaxies that appear as smooth, glowing orbs of stars. And irregular galaxies shaped by gravitational chaos. Yet every so often, astronomers stumble upon something so unusual that it challenges our understanding of cosmic structure itself. And one of the most striking examples is the enigmatic Hoag's object, a rare and beautiful ring galaxy discovered in 1950 by Arthur Hoag. At first glance, Hoag-AS object looks almost artificial, a nearly perfect circle of bright blue stars surrounding a faint yellowish core, with an empty dark gap separating the two regions. This bizarre geometry defies easy classification because galaxies are not supposed to form such clean rings naturally. And even after decades of study, its origin remains a mystery that continues to puzzle astrophysicists. What makes Hoag-AS object even more fascinating is its sheer precision. The outer ring is made up of hot young stars, glowing blue from recent bursts of star formation, while the central core contains much older red and yellow stars, suggesting two distinct epochs of stellar evolution, somehow separated by a vast void. How could such a structure come into existence? Several theories have been proposed, each carrying profound implications for how galaxies interact, evolve, and recycle their material. One leading explanation is that Hoag's object may have formed through a rare galactic collision, where a smaller galaxy passed directly through the center of a larger one billions of years ago. The gravitational shock waves from such an impact would have rippled outward like a stone dropped into water, compressing gas into a circular wavefront that ignited a burst of star formation, leaving behind the luminous outer ring we see today. If true, Hoag's object would be a frozen moment in time, a galactic ripple still visible across millions of light years. But there are problems with this idea. Most collision-induced ring galaxies show some evidence of the intruding galaxy either as a remnant core or tidal features stretching into space. Yet in Hoag's object, no such culprit has ever been found. The central region is isolated, calm, and strangely symmetric, giving no obvious clues of a violent past. Another possibility is that Hoag's object is the result of bar instability, where an internal bar of stars within a spiral galaxy collapses or redistributes material outward, forming a ring. But again, the geometry of Hoag's object is too perfect, too detached, and unlike the typical resonant rings seen in barred spirals. Some researchers have even speculated that its unusual symmetry might hint at exotic processes, perhaps involving dark matter shaping the distribution of visible stars in ways we do not yet understand. Whatever the cause, Hoag's object is not alone. Other ring galaxies exist, though they are exceedingly rare compared to spirals and ellipticals. Each one serves as a cosmic laboratory, offering insights into galactic dynamics, star formation, and the hidden scaffolding of dark matter that underlies the visible universe. The study of Hoag-AS object is also a reminder of how much we still have to learn. With modern telescopes like Hubble and now the James Webb Space Telescope, astronomers can peer deeper into its structure, analyzing the light from its stars to determine their ages, compositions, and motions. Such data can reveal whether the stars in the outer ring are truly the product of a collision shock wave, or if they formed through more gradual processes. The central core, too, holds secrets. Its composition may reveal whether it is the remnant of a disrupted galaxy or simply the surviving heart of a larger spiral. Beyond its physical origin, Hoag's object also captures the imagination because of its almost uncanny appearance. Some astronomers have joked that it looks like a cosmic bullseye or a galaxy within a halo, while others note that its symmetry is so striking it could almost be mistaken for a piece of abstract art painted across the night sky. It is a humbling reminder that nature often creates structures that challenge our expectations and force us to question our models. For the broader search for life, Hoag's object may not directly play a role, but its existence underscores the diversity of environments in the universe, some of which may host conditions radically different from those in our Milky Way. If ring galaxies are the result of collisions, then they may host bursts of star formation and planetary systems shaped by gravitational chaos. Environments that could either foster or hinder the emergence of life, depending on the stability of those systems. In that sense, Hoag's object is not just a curiosity. It is part of the grand story of cosmic evolution, a reminder that galaxies are not static islands, but living entities shaped by time, gravity, and chance encounters. As future observatories probe deeper, perhaps even resolving planetary systems in distant galaxies, the significance of such unusual structures may grow. For now, Hoag's object remains a mystery suspended in the night, a cosmic question mark that defies easy answers. And perhaps that is what makes it so compelling. In a universe where we often categorize, classify, and predict, there remain objects that resist explanation, challenging us to look closer, think deeper, and accept that the cosmos still holds wonders beyond our imagination. The search for understanding is not just about solving puzzles. It is about appreciating the beauty of those puzzles, the elegance of the unknown, and the thrill of standing at the edge of human knowledge, staring into the abyss of mystery. Hoag's object, with its luminous ring and silent core, embodies this spirit, inviting us to wonder not just how galaxies form, but why the universe is capable of producing such haunting perfection in the first place. Mars Mysteries. Brain terrain, atmosphere, and climate. Mars has long captured humanity's imagination, not only because it is our closest planetary neighbor, but also because its surface tells a story of a world that might once have resembled Earth, and yet now lies barren, frozen, and silent. And among the many enigmas scattered across its deserts, canyons, and polar regions, few are as strange as the so-called brain terrain, a puzzling pattern of ridges and troughs etched into the Martian landscape that resemble the convoluted folds of a human brain. First identified in high-resolution images from orbiting spacecraft, brain terrain appears most often near the mid-latitudes and polar regions, areas where scientists believe buried ice lies just beneath the surface. The ridges twist and curl into patterns eerily similar to cerebral cortex folds. And while the resemblance is coincidental, it hints at a complex geological and climatic process at work beneath Mars's frozen skin. Current theories suggest that brain terrain may form as buried ice slowly sublimates, turning directly from solid to gas, causing the overlying soil to collapse and crack in intricate patterns. Over time, repeated cycles of freezing and sublimation sculpt the landscape into these strange, brain-like textures. This process tells us not only about the presence of subsurface ice, but also about the dynamic climate history of Mars, a planet that has swung between wetter and drier, warmer and colder periods over millions of years. The existence of such features indicates that Mars is not entirely geologically dead. Rather, it still undergoes subtle but significant surface changes driven by its climate and the presence of volatile compounds like water and carbon dioxide. Beyond brain terrain, Mars presents an even deeper puzzle through its thin, fragile atmosphere, which today is less than 1% the density of Earth's, composed mostly of carbon dioxide with only trace amounts of nitrogen and argon. Such an atmosphere cannot support liquid water on the surface for long, as it either freezes or evaporates into space. Yet the ancient river valleys, deltas, and mineral deposits across Mars testify that billions of years ago, water flowed abundantly across its surface. What happened to Mars's atmosphere? The leading theory is that the planet lost its global magnetic field early in its history, leaving it exposed to the relentless solar wind. Over billions of years, charged particles streaming from the sun stripped away much of the Martian atmosphere, thinning it to the wisp we see today. This catastrophic loss transformed Mars from a world that may have supported lakes, rivers, and perhaps even oceans into the cold desert we now observe. Now, NASA's MAVEN mission has provided direct evidence of this atmospheric stripping, showing how particles are still being blown away into space, an ongoing process that continues to erode what little remains. The climate, too, reflects this loss. Without a thick atmosphere to trap heat, Mars experiences extreme temperature swings, with daytime highs near the equator occasionally climbing above freezing, only to plummet to bone-cracking lows of 100 degrees Fahrenheit at night. Seasonal changes driven by carbon dioxide cycles at the poles add another layer of complexity. Each winter, carbon dioxide in the atmosphere freezes out as dry ice, forming vast polar caps that later sublimate back into gas in spring, driving fierce winds, dust storms, and pressure shifts across the planet. These processes reshape the surface, carve dunes, and transport dust globally, sometimes shrouding the entire planet in storms that last for weeks. The largest of these dust storms can engulf Mars in a reddish haze, a reminder that even without tectonic plates or abundant volcanism, the planet remains active in its own way. And yet, the mystery of Mars is not simply geological, it is also astrobiological. Could microbial life have once thrived during its wetter past, sheltered in underground aquifers, or clinging to hydrothermal vents beneath ancient seas? Could some of that life persist today, hidden beneath layers of ice or deep underground where liquid water might still exist? The brain terrain features, with their association with subsurface ice, raise tantalizing possibilities. If liquid water occasionally forms within or beneath these icy deposits, even temporarily, it could provide a habitat for extremophils, organisms similar to those on Earth that survive in glaciers, permafrost, and deep subsurface environments. For planetary scientists, Mars is thus a paradox. It appears dead on the surface, yet whispers of activity remain, from sublimating ice to shifting dunes to seasonal methane detections in the atmosphere that some researchers suggest could be biological in origin, though geological explanations remain plausible. The thin atmosphere, while inhospitable to humans without protection, offers clues to the planet's past and potential future. If we could somehow restore it through terraforming or technological intervention, Mars might once again support liquid water and perhaps even agriculture. But achieving this would require staggering amounts of energy and resources, and current studies suggest that much of the lost atmosphere is gone forever, making full-scale terraforming unlikely with near-term technology. Still, Mars continues to inspire because it is familiar yet alien, close yet unreachable, promising yet harsh. Its mysteries, the brain terrain, the lost atmosphere, the frozen climate, are not just scientific curiosities, but keys to understanding planetary evolution itself. By studying Mars, we learn how planets change, how they succeed or fail at sustaining habitability, and ultimately, what makes Earth unique. For the search for life, Mars is a natural first target. Robotic explorers like Perseverance and Curiosity scour its surface, sampling rocks, analyzing soils, and searching for signs of past microbial life. Future missions may bring samples back to Earth, where laboratories can probe them for organic molecules and microscopic fossils. If Mars ever hosted life, even briefly, it would profoundly alter our understanding of biology, proving that life is not unique to Earth and that the universe may be more alive than silent. And if Mars never hosted life, then its silence will teach us something equally profound, that even a planet so similar to Earth in many respects can fail to nurture biology, reminding us of the fragility of habitability, the brain terrain, the eroded valleys, the thin breath of atmosphere clinging to the planet. All are chapters in a story that humanity is only beginning to read. With every rover that crawls its surface, with every orbiter that maps its skies, we peel back another layer of that story, guided by the hope that Mars will eventually reveal not only its own secrets, but also the deeper truths of life in the cosmos. Time travel, science, paradoxes, and theories. Time travel has fascinated humanity for centuries, blurring the line between science and imagination. And while it has long been the subject of myths, novels, and Hollywood films, modern physics has forced us to confront the question seriously. Is time travel possible within the laws of nature? To answer this, we must begin with Einstein's theory of relativity, which revolutionized our understanding of space and time by uniting them into a single continuum known as space-time. According to special relativity, time is not absolute but relative, flowing at different rates depending on one's speed and gravitational field. This effect, called time dilation, has been proven in experiments where atomic clocks flown on airplanes or placed in orbit run slightly slower than identical clocks on Earth. On a human scale, these differences are tiny, but at near-light speeds, or in the presence of immense gravity, they become profound. In principle, this means traveling into the future is already possible. An astronaut on a journey near the speed of light could return to Earth to find that centuries have passed, while they aged only a few years. But what about traveling into the past? Here the challenge becomes thornier, raising paradoxes that threaten to unravel causality itself. The so-called grandfather paradox asks what would happen if a time traveler went back and prevented their own grandparents from meeting, thereby erasing their own existence. Such contradictions suggest that backward time travel may be forbidden, or at least constrained in ways we do not yet understand. Nevertheless, general relativity allows solutions that seem to permit it. Einstein-ES equations describe not only expanding universes and black holes, but also hypothetical structures called closed time-like curves, paths through space-time that loop back on themselves. One example is the rotating universe model proposed by Kurt Gödel, which in theory would allow a traveler to return to their own past. Another involves wormholes, tunnels through space-time connecting distant points, which could, if stabilized, function as time machines by linking two regions where time flows differently. The catch is that wormholes may require exotic matter with negative energy density to remain open, something we have no evidence exists in usable form. Even if they did, quantum effects might destroy them the instant anyone tried to use them. Other proposals include cosmic strings, hypothetical one-dimensional defects in space-time that, if massive enough and moving near the speed of light, could bend space-time into loops permitting time travel. Yet each scenario collides with enormous practical barriers, not least of which is energy. Time machines of these kinds would require power on scales rivaling entire galaxies. Beyond technical limits, there is the question of logic. Some physicists argue that the universe enforces a chronology protection conjecture, a term coined by Stephen Hawking, meaning that the laws of physics conspire to prevent time paradoxes by forbidding closed time-like curves. In this view, backward time travel is impossible, preserving causality as a bedrock principle. Others suggest that paradoxes might be avoided through self-consistency. Events in the past cannot be changed because whatever actions a time traveler takes were always part of history. This so-called Novikov self-consistency principle imagines time as fixed and unchangeable, a single block where free will is constrained to maintain coherence. Still others invoke the many worlds interpretation of quantum mechanics, in which traveling into the past would not alter one's own history, but instead branch into an alternate timeline. In this scenario, a traveler could prevent their grandparents from meeting, but only in a parallel universe, leaving their own origin untouched. Each possibility is mind-bending, pushing against our intuitions of reality. Experimental hints sometimes deepen the mystery. Quantum entanglement, where particles remain correlated across vast distances, has led some to speculate about retrocausality, the idea that effects might influence causes. Though mainstream physics does not interpret entanglement this way, it shows that our classical notions of time may be incomplete. Similarly, phenomena near black holes stretch our understanding of causality. At the event horizon, time slows to a crawl relative to distant observers, and within, our current physics cannot describe events at all. Could black holes connect to other regions of space-time, perhaps even other times? The mathematics allows speculation, though evidence is absent. What we do know is that time travel into the future is real, observable, and inevitable through relativity, while travel into the past remains an open question, balanced between mathematical possibility and logical impossibility. Philosophically, time travel forces us to reconsider free will, destiny, and the nature of reality. If the future already exists, does that mean it is predetermined? If the past can never be altered, are we prisoners of a fixed timeline? Or does quantum uncertainty grant true openness, branching possibilities that only resolve when choices are made? Science fiction often plays with these ideas, offering narratives where travelers rewrite history or glimpse futures they struggle to avoid. In reality, the truth may be stranger still, for the ultimate nature of time remains one of the deepest mysteries in physics. Cosmology tells us that time itself began with the Big Bang 13.8 billion years ago, yet what existed before, if anything, remains unknown. Some theories suggest time is emergent, not fundamental, arising from deeper quantum processes. If so, our dream of mastering time may be as naive as a fish dreaming of mastering water. And yet, the pursuit of time travel research has profound value, even if practical machines remain forever out of reach. It pushes technology, mathematics, and philosophy forward, uniting disciplines in pursuit of answers. It inspires humanity to look beyond the present, to imagine futures and pasts not as chains, but as canvases of possibility. Whether or not time machines are ever built, the exploration of time travel enriches our understanding of relativity, quantum mechanics, and cosmology. It reminds us that the universe is stranger than we can imagine, that the boundary between science and imagination is porous, and that the quest to understand time is as much about understanding ourselves. For if time travel were possible, what would we seek to change, to revisit, to undo? And if it is not, then perhaps the lesson is to cherish the present as our only true moment. In either case, the mystery of time remains an open frontier, a dimension we inhabit yet barely comprehend, inviting us to continue questioning, dreaming, and searching. Cosmic strings, wormholes, quantum mechanics, and future possibilities. In the quest to understand the ultimate boundaries of physics, humanity has imagined extraordinary structures that might bend, twist, or even break our conventional view of reality. And among these cosmic strings and wormholes stand as some of the most fascinating theoretical constructs, bridging the frontier between science fiction and rigorous mathematics. Cosmic strings are hypothetical one-dimensional defects in space-time, predicted by certain grand unified theories of particle physics, thought to have formed in the early universe during symmetry-breaking phase, transitions just fractions of a second after the Big Bang. If they exist, they would be unimaginably thin, yet incredibly dense, with a single cosmic string perhaps stretching across the universe while packing more mass per unit length than entire galaxies. Their gravitational effects would be profound. Passing near a cosmic string could cause space-time to warp in such a way that paths loop back on themselves, potentially allowing forms of time travel or shortcuts across space. But despite decades of searching, no evidence for cosmic strings has yet been found, though some astronomers still scan the cosmos for their telltale gravitational lensing signatures, double images of distant galaxies created by the warping of light around these invisible filaments. Wormholes, on the other hand, were first conceived as mathematical solutions to Einstein's equations of general relativity, describing tunnels that connect two distant points in space-time. In principle, a wormhole could allow instantaneous travel between stars or even between universes, collapsing vast cosmic distances into a single step. The idea is seductive, offering a solution to interstellar travel and perhaps even a gateway to time travel, since linking 2 points with different time flows could effectively create a time machine. Yet wormholes come with daunting problems. The simplest versions collapse almost instantly, pinching shut before anything can pass through. To hold them open would require exotic matter with negative energy density, something permitted by quantum theory in small amounts, but never observed on scales large enough to stabilize a wormhole. Quantum mechanics itself deepens the mystery. At the smallest scales, space-time is thought to froth with fluctuations, a seething foam where wormhole-like connections may constantly appear and vanish in Planck time intervals. Some theorists suggest that this quantum foam could, in principle, be harnessed to create or enlarge wormholes, though such an achievement lies far beyond any technology we can conceive today. Quantum theory also raises the possibility of entanglement-based connections, leading to the provocative idea known as ER-EPR, proposed by physicists Juan Maldacena and Leonard Susskind, which suggests that entangled particles might be connected by tiny non-traversable wormholes. If true, this would hint at a deep unity between the geometry of space-time and the information structure of quantum mechanics, a unity that could someday illuminate how gravity and quantum theory merge into a single framework. These ideas remain speculative, yet they push us closer to understanding the true nature of reality. Looking ahead, the future possibilities are staggering. If exotic matter can be engineered, stable wormholes might allow interstellar travel not in centuries, but in moments. Cosmic strings, if they exist, could be manipulated to bend time, offering humanity a glimpse of futures or pasts beyond imagination. Even if such technologies remain forever out of reach, the pursuit of these concepts enriches science. It forces us to confront paradoxes, to refine our theories, and to test the limits of observation. Already, gravitational wave observatories like LIGO and Virgo are sensitive enough to potentially detect cosmic string vibrations, while space telescopes scan the heavens for unusual lensing patterns. Each null result teaches us more about what the universe is not, narrowing the possibilities and sharpening the questions. Philosophically, the exploration of cosmic strings and wormholes speaks to humanity's deepest drive, the refusal to accept limits. For thousands of years, we gazed at the stars and believed them unreachable, only to build rockets that carried us to the moon. Today, interstellar travel seems impossible, but perhaps it is only a matter of perspective, awaiting breakthroughs in physics as profound as relativity or quantum mechanics once were. The path forward will demand imagination, patience, and humility. We must remember that the universe does not bend to our desires. Its laws are what they are, and it is our task to uncover them, not impose them. Still, even if wormholes and cosmic strings remain forever hypothetical, the journey of studying them expands our intellectual horizons, reminding us that the cosmos is stranger and richer than our everyday experience suggests. For the search for extraterrestrial civilizations, these concepts offer one more possibility. Perhaps advanced beings, if they exist long ago, learned to exploit such structures, leaving us blind to their presence because they do not travel through ordinary space, but through hidden corridors of space-time. This could even form part of the solution to the Fermi Paradox. Civilizations may not be absent, only inaccessible, inhabiting a realm of physics we have yet to master. In the end, the pursuit of cosmic strings, wormholes, and quantum possibilities is about more than travel or technology. It is about confronting the deepest questions of existence. What is time? What is space? Is the universe finite or infinite? Do parallel realities exist? And if so, can we reach them? Each step toward answering these questions, whether through mathematics, observation, or experiment, is a step toward understanding not just the universe, but our place within it. The future of physics will likely reveal surprises beyond even our wildest theories today. But what unites all of them is the same flame of curiosity that drove our ancestors to look up at the night sky. Whether or not humanity ever walks through a wormhole or harnesses the power of a cosmic string, the very act of exploring these ideas fulfills something essential about who we are. Beings who dream beyond horizons, who question boundaries, and who seek the infinite in a universe that may itself be boundless.